These are the 6.12 and 6.21 notes. I'm going to be covering area of a sector of a circle and the unit circle. Now, these notes are going to seem a little bit bizarre. Only the first two slides are going to apply to tonight's homework, and the last four are going to be based on things that we're going to see in the future. This is not the way that I would ideally present this in class, but since we're having to do this remote learning, I'm going to make these notes to be a little bit more in bite-sized chunks for you guys. So the unit circle is not the easiest thing in the world. It takes a little bit of time to wrap your head around. I love it. However, I understand that it's a lot of information and I cannot just throw it all at you in one notes. I'm going to break this down over three. So today I'm going to kind of finish up what we did in that last section, and then we'll start looking at this unit circle over the next 3 days with a few assignments. And you'll see what this looks like. It'll take some time, but I don't want you to freak out if you don't understand the end of today's notes or you're not sure what's going on. That's normal. You're going to have 3 full lessons on it to go over all the information, and we'll work with each other. Again, you can always ask me questions. So let's start getting into it now. So this is 6.1 part 2 to finish up. We're going to talk about the area of a sector of a circle. Now, you guys have been finding the area of full circles since like 5th grade. And you learned in 5th grade that the area of a full circle is pi r squared. Well, let's say that I don't want to know what the area of a full circle is. I want to know what the area of a sector of a circle is. And why would I want to know the area of a sector? Let's say that I'm splitting 8 slices of pizza with an odd number of people. Let's say that I have got 3 people that I want to split 8 slices of pizza with. And we want to make sure we're as close to even as we can get. Now, you all know pizzas. They're never cut perfectly. We don't have perfect 1/8 of a pizza every time they're sliced. Pizza workers just really quickly put the pizza cutter through, and you have all these different slices that have different areas. I could go through, I could measure the angle of each, and I could know the radius of my pizza, and then I could figure out what is the area of each slice of pizza. And then me and my friends, we could decide how are we going to divide this up so the 3 of us get as close to equal amounts of pizza as possible. And here's how we do that. We had this formula similar on the arc length last week. Now we're going to look at it for area. If I compare a ratio of 2 thetas, it's going to be the same as a ratio of 2 angles given the same radius. And so what I can say is, all right, let's take this ratio here. And as opposed to putting theta 1, let's say that I'm talking about a full circle, which we learned last week can be represented by 2 pi radians. Well, that means that if I have a theta 1 of 2 pi radians, the area of that theta has to be pi r squared, because we've already learned that the area of an entire circle is pi r squared. I'll cross multiply here. And I will say that a times 2 pi is equal to theta times pi r squared. I'll divide both sides by 2 pi. Those will cross out, and I'll be left with a is equal to 1/2 theta r squared. So the area of any sector of a circle can be defined as 1/2 of theta pi r squared. And this works. I can do a quick check to prove this. If I say that I'm looking for the full circle, I can say a is equal to 1/2 of that 2 pi radians times r squared. That crosses out, and I'm left with a is equal to pi r squared. So now I know that the area of a sector formula makes sense, because if my sector is the full circle, it works out. It's that formula that I've learned all the way in 5th and 6th grade. So I've got an example here. Find the area of the sector of a circle with a radius of 2 feet formed by an angle of 30 degrees, and then round this answer to 2 decimal places. What I'm going to do here is, first, I've got my angle, or my theta value, of 30 degrees. I've got my radius of 2 feet. And what I'm looking for is the area of my circle. I'm not sure what the area of my circle is. That's my goal, is to figure this out. So, first things first, this needs to be in radians. You've always calculated this in radians. Pi r squared is radians. When you did this back in 5th and 6th grade, when you were just learning these formulas of the basics of a circle, you were just plugging in pi r squared. And nobody ever explained to you that you're doing this in a radian value, not a degree value, and that's not the fault of your 5th or 6th grade teachers. This is way too complex for just a 10 or 11-year-old to wrap their mind around this. There's a lot of different things going on here. Now that we're older, now that we've had a lot of experience with math, learning this trig, knowing these formulas being based on radians is something well within your capability. So now that you know that you've been doing work with radians your entire life, this should be a little bit easier. I'm going to take this 30 degrees. I'm going to multiply it by pi over 180, because this is how I convert my degrees to radians. 30 degrees goes to 180 degrees 6 times, so I've got pi over 6 radians. Now to figure out the area, I'm just going to plug and chug because I've got my formula. The area is equal to 1/2 times 2 feet squared times that theta of pi over 6. I've got my area is equal to 1/2 times 4 feet squared times pi over 6. Area is equal to 2 feet squared times pi over 6. Area is equal to pi over 3 feet squared. And then if I wanted to round this to 2 decimal places, I'm just going to go into my calculator and I'm going to type pi divided by 3. So give me a second here, because I don't know what pi divided by 3 is off the top of my head. I'm going to plug that into my handy dandy calculator. And I'm going to end up with my area is about 1.05 feet squared. And that's my answer. These are all plug and chug formulas. Not the hardest thing in the world. You just have to know where everything goes, and then you're going to solve for your variables. I'm not going to break this down and create a bunch of different formulas out of this. I'm going to use one and solve for missing variables as needed. You'll see a couple examples of this on your homework, so don't worry too much about that one. All right, so that's all we have to do for the area of a sector of a circle. Now this is the last thing you'll see on tonight's homework. Tonight's homework consists of a little bit of a review of last week. You'll be converting radians and degrees again. You'll be doing arc length of a circle, which we learned last week but didn't practice. And then you'll be doing area of the sector of the circle, which you're learning today. From this point on, I'm moving into the unit circle. And you're not going to have anything on your homework from the unit circle yet. You'll have 2 homework assignments on the basics of the unit circle this Thursday and next Monday. But I'm going to start introducing it now because, again, I want to give this to you in bite-sized chunks. There's a lot of information here. Now, I love the unit circle. I tell people all the time, if I were ever to get a tattoo, I would get a tattoo of the unit circle. Sometimes when I'm bored, I will just draw out the unit circle and I'll start thinking about the way they relate to each other. There is just so much information which can be discerned from the unit circle. It is this beautiful, beautiful part of mathematics. It just has so much information in it, and it is such a simple thing that can just be blown up to be so complex. You can get so many little pieces of information about the universe, about our world, just from this one circle with a radius of 1. It is fantastic. It's one of my favorite subjects in math. You'll find a lot of mathematicians who've spent their entire lives studying this, and there are quite a few other mathematicians who think that this is the coolest thing that they've ever studied. I might be weird in thinking that, but in the math world, I'm not weird in thinking this. Now, what is the unit circle, though? What is this thing that Mr. Yehlen is in love with? The unit circle allows us to consider the right angle trigonometry for any right triangle, and we can relate the cosine and sine values to the xy values which are found in the circumference of the circle. The radius of the circle will always be treated as the hypotenuse of the triangle within, and that's with respect to the x-axis. So that means the right angle always lies on the x-axis across from the angle at the origin. And the radius is always 1, which makes it easy for us to calculate our trig values. So here's kind of a representation of just what that circle is. We've got a radius of 1, and that is going to exist all the way around the circle, and you can see that with that radius of 1, we'll have our points 1, 0, 0, 1, negative 1, 0, and 0, negative 1 on our x and y axis, depending on if we're positive or negative. Now this is what it actually looks like when we're talking about the right triangles. We are forming right triangles within this circle, and it's going to be drawn with respect to the x-axis, meaning that I have this right triangle here across from the origin. What this allows me to do is I can see that I have got a height here of y distance. Well, just kind of based off how this works, I'm going to end up with a point y. Whatever the height of my y of the triangle is just there. And what that allows me to say is that the y value of my coordinate is going to be equal to my opposite side. Just like down here, I've got a width, a base of x. And that is going to end up corresponding with the point x on the circumference. So I've got a point xy which exists, because however far out I go and however high up I go is going to give me a point xy, and that allows me to make my x my adjacent side. Because the theta I'm concerned with is always going to be this theta here. It's always going to be the theta which arises in the origin of this circle. There is another angle in this triangle which we're not considering. We have this angle up here which I could label as alpha. However, I'm not thinking about that angle in the unit circle. I might start using that angle in the future, an application of a few problems, but for right now, this angle here, that's the angle that we're concerned about. That is everything that we want to think about in the unit circle, is the angle which is arising from this origin in the unit circle. All right, so let's start thinking about this. There are two very common right triangles, the 30, 60, 90 and the 45, 45, 90. And this actually allows us to look at three triangles within each coordinate, or within each quadrant. One is going to have my 30-degree angle here. So when I'm talking about theta, this will be my 30 degree, and up here will be that like alpha value, but this will be 60 degrees. The other 30, 60, 90, I'll have that 60 degree in the origin, and then I'll have my 30 degree up here. So I can use my 30, 60, 90 degree triangle twice. It's just a matter of which angle I'm putting in the origin compared to the other. My last one is my 45, 45, 90. Since that's an isosceles triangle, it doesn't matter which one is up top and which one is at the origin because they look the exact same. So I've got three triangles which are formed in each quadrant. And these triangles are going to form in every single quadrant over and over and over. Now this is a little bit complex here, and where I'm going to be referencing this information many, many times throughout these notes, is that I've got right triangles in every quadrant. Now I'm going to be drawing my angles like this. I'll go back up to this previous slide. I've still got my coordinate system that looks like this. And when I draw my angles, I'm going to have my initial side that occurs here. But let's say that I've got an angle going out in quadrant 3. It would look like this. So that would be what my angle is. However, I'm actually going to break this angle down, how it relates to this x-axis here, because that's closer to the terminal side. So I'm going to be able to think about the fact that it still has an opposite and it still has an adjacent like this. And I'm going to be able to think about its xy coordinate that way. And so the angle is still going to relate to this close x-axis, even though it's drawn from this initial side. For those of you who have taken physics, you've seen this a lot, especially if you're in honors physics. You've seen this quite a few times, and you've seen the fact that we're breaking our angles down differently depending on where they lie. So this is an angle which is greater than 90 degrees, but I'm still drawing it with relation to my x-axis. And this visual down here is just showing you that. If I have a radius of root 2, so this isn't a unit circle, I could still have a 45-degree angle. It's just going to be a matter of how long my x or y's are. So you'll see in quadrant 1, I've got a positive x, positive y, root 2, negative x, positive y, root 2. All of these still have those values of 1. My sign changes. All of them still have 45-degree angles. But I'm just measuring it with respect to my closest x-axis, and those right angles are always found opposite the origin. So I'm never going to be considering, like, there's never going to be a right angle up here. That's not going to happen. There's never going to be my right angle here. That's not what I'm looking for. My right angle always occurs opposite the origin, and I'm going to be able to measure all of my angles that way. Now I'm going to introduce you to every angle in the unit circle. Now, at the end, I'm going to start going over the theory of how some of these angles relate, but right now I'm just going to write them out for you. I'm going to do this fairly quickly, and you might wonder how I am doing this fairly quickly. I learned this the first time when I was 14 years old, so I've been doing this for half my life at this point. It is well ingrained in my memory. It's seared in my memory, and you would expect anything I'd want a tattoo of, I'm going to have it memorized pretty well. I'm just going to put every degree on this unit circle in degrees, or every angle in degrees, because you guys have worked with degrees a lot more than you've worked with radians. Starts at 0 degrees, goes to 30 degrees, 45 degrees, and 60 degrees. And then we already know that a quarter revolution is 90 degrees. You guys learned that last week. So now that I know this, I can start thinking about some patterns of this. The first, as I move from my x-axis to my first angle, I add 30 degrees. And then I've got a 30-degree difference between this 60-degree and this 30-degree angle here. I've got a 45-degree difference between that first angle and the middle angle of each quadrant. And then finally, I've got a 30-degree difference between my axis and my next angle. So whenever I move from an angle to an axis, I'm moving at 30 degrees, and the middle to that axis is 45 degrees. So I'm going to add 30 degrees here. That's going to be 120 degrees. This angle, I'm going to add 45 to that 90 degrees to get 135 degrees. This next angle, I'll add 30 degrees to that 120 degrees to get 150 degrees. And this last angle, I'm going to add 30 degrees to get 180 degrees. And when you look at that, we've already established that half of a rotation is 180 degrees, so this pattern holds up for me. I'm going to continue this pattern. Add 30 degrees to get 210 degrees. Add 45 degrees to 180 to get 225 degrees, and add 30 degrees to that 210 to get 240 degrees. Add another 30 degrees to that 240 degrees to get 270 degrees, and we learned last week that 3/4 of a revolution was 270 degrees, and 270 degrees is 180 degrees plus 90 degrees, so this pattern still holds up for me. I'm very happy with where I'm at. I can add 30 degrees here to get 300 degrees. I can add 45 degrees to that 270 degrees to get 315 degrees, and I can add 30 degrees to that 300 degrees to get 330 degrees, and then finally at 360 degrees over here, which we already know is a full revolution, and you've known that's a full revolution probably since you were like 7. So now I've done a lot of work here to prove, all right, all of these angles make sense based off of how they relate to that x-axis and how they relate to their axes. Now I'm going to put all of these in radians. So I'm going to define that my pink value, so pink are radian values. And I could go through the conversion of all of these, but I'm not going to think so much about the conversion. I gave you a chart at the end of last week's notes that have converted all of these angles. These are the big unit circle angles. So I'm just going to go through. This is pi over 6, pi over 4, and pi over 3. 90 degrees is pi over 2. This is 2 pi over 3. This is 3 pi over 4. This is 5 pi over 6. This is pi. We learned last week that pi revolutions was half of a revolution of a full circle. So we now know that if I'm looking at pi radians, I'm looking at half of a revolution. Down here, I've got 7 pi over 6. I've got 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, 11 pi over 6, and then 2 pi, which we learned last week was full revolutions. This is also 0 degrees radian if I don't move at all. So now I have every single angle of this unit circle in both degrees and radians. Again, I went through those radians quickly. I've been doing this unit circle a long time. I know it like the back of my hand. I could go over a couple patterns here. Like for instance, you'll see that all of your pi over 6 are the closest angle to your x-axis. Everything that's a pi over 4 is your next closest angle to your x-axis. And then everything that's pi over 3 is going to be your farthest angle from the x-axis. You can convert all these degrees to radians to get these radian values as well. I would make sure that you have this for reference whenever you're working. For you guys, especially with this remote learning, any assessment you have, any homework you have, you're going to have this unit circle on you. You're going to be able to work with this unit circle. So I would make sure that you're using it every single chance that you get. This is a great reference to have. We're going to be working with radians mostly. And these are the kind of the patterns you'll see, and I'll get more and more into this as we have notes on Thursday and next Monday. But this is your basic introduction to the unit circle. At this point, you now know every angle in degrees and radians, which is good. And we're going to start looking at this more and more on Thursday. This is for your homework for tonight. Again, this covers last week's lesson as well as just the area of a circle for today. The unit circle doesn't show up until Thursday's activity, and you'll see what that is then. If you have any questions, please reach out sooner rather than later. We can set up a meeting very, very easily. So let's make sure we get that done if you have any questions. Thank you. Have a good night.